In the first video on carbon cycling, we looked at natural processes and how they distribute carbon over the face of the earth. And we also looked at the time scale, and we incorporated ocean circulation into our understanding of how carbon moves and how long it takes it to complete the cycle. This video, we're going to look at how human activities affect the carbon cycle, how they are affecting the distribution in terms of how much carbon is, say, in the atmosphere, oceans, or biosphere, and also how they're affecting the fluxes and disturbing the balance and steady state of the carbon cycle. And so before we get to that, let's just do a quick budget of our carbon in terms of human activities. So we're going to look at the sources of carbon that we put into the environment and also the sinks. Where does that carbon actually end up? And so these numbers are a couple decades old, but they still give us an idea of where it's coming from and where it's going. As we go through this, pay attention to the errors as well. The errors help us understand how easy it is to make these measurements, or I should say how difficult as well. And so in terms of sources, we're looking at two primary sources: the burning of fossil fuels, which is higher than deforestation. Now, when we say deforestation, what we mean in terms of a source is it's not that we are just removing that carbon from the forest. We're removing a we're removing a sink, essentially a sink for carbon. And by removing that sink that would actually draw in the CO2, we're actually adding it as a source. And so when we think about these sources of carbon, about 50% of the CO2 from fossil fuels remains in the atmosphere. So we can imagine that the carbon dioxide in the atmosphere is building as we continue to burn fossil fuels. But 30% of the CO2 that we've produced since the Industrial Revolution is actually in the ocean. So much of it also gets sucked into the ocean. The ocean is basic in terms of its pH, and so it acts like a sponge in terms of drawing in CO2 into the water and converts it to bicarbonate. So we're seeing about an increase of 1% per year to the atmosphere, and we're also, just to make it relative, all that combustion has consumed 0.05% of the oxygen from the atmosphere. Very, very small amount, but nonetheless, it is also affecting the amount of oxygen. So where is it going? Again, the sinks, it's the atmosphere, which we can measure fairly well, the oceans, and also we don't know. The unknown sink, 1.7 plus or minus 1.4. We don't even know the unknown very well. And what they most likely think this is probably the transfer of particles from the surface waters of the ocean to the deep water. So if we don't know our fluxes very well, then we have a hard time knowing what the sinks are. And so we think it's either in the transfer of organic material from the surface waters to the deep water in the ocean, or others believe that it is just getting locked up in the biota, and we're not measuring it. So let's take what we know about the carbon cycle and the fact that it does take 2,000 years for the cycle to completely turn over. And let's think about the activities that we're doing today in terms of burning of fossil fuels and emitting that carbon into the atmosphere. And so what I have in this plot is I have the amount of carbon that we burn every year, and this is in gigatons. And if you have your notes available, you may need to change this axis. I've modified it in this presentation to be what it should be. Nonetheless, what we see is that we are still exponentially increasing our use of fossil fuels, but there will be a point in the future, in some point in the next century, as least that's what the models say, that we'll reach a maximum for whatever reason. I don't know if this is because of alternative energy or due to changes in population, but what they, or even ability to extract oil, but nonetheless, they do believe that we will slowly stop using fossil fuels over the next 500 years. Now we're at about 2,500 there. And over that same period of time, what we see is an increase in the CO2 in the atmosphere. That's what this bottom plot shows. And so currently we're above 400 parts per million. And what I want to show from this is that even when we reach our maximum, that would be about right here, we reach our maximum, the CO2 concentration in the atmosphere will continue to increase. There's going to be this delayed response. The system will get disturbed by putting all this CO2 into the environment through the combustion of fossil fuels. Here I'm using octane as a generic molecule to show the reaction for the combustion. But nonetheless, it's going to take hundreds of more years for it to stabilize. And that's, again, due to the cycling, the fact that the CO2 needs to get incorporated into the biota, into the deep ocean, and then it slowly starts to level off. And once it does level off, it's going to level off at a totally new value, somewhere near 1,000 parts per million, that is different than before the disturbance. Before the disturbance, again, for the last 200,000 years, the concentration of CO2 in the atmosphere was between 200 and 280 parts per million. When this is all over, when we've completely damaged the earth, and again for thousands of years, it will be at a much higher concentration, which will definitely affect future climate. And what we can also say is that the levels that we're seeing in the atmosphere that are close to 1,000 ppm, we have not seen, or I should say the Earth has not seen those types of concentrations for close to 420,000 years. Even more disturbing, and a lot of times it's not really mentioned, it's the rate of change. The fact that today what we're doing by burning all these fossil fuels is 100 times quicker than what was experienced a 500,000 years ago. So what we're doing and how we're doing it is unprecedented. And so what we've already done has damaged the earth. And there's no going back at this point, at least not in our lifetime and not in the next, 10 or 20 generations. We have affected those future people and the climate that they'll live in. And so I got that plot from this paper, and this again is showing the emissions, the CO2 concentration over the years. But what I want to mention as well, it's not just about climate, it's about ocean acidification. And so this paper was modeling what these CO2 concentrations will do to the pH of the ocean over time. And so here we are, right here, we're starting to see the effect, a slight change in pH in the surface waters of the ocean. But as we see over the next 100 years, we're going to most likely see a change of 0.4 pH units, which will be disastrous for the biota in the ocean. Anything with a calcium carbonate shell, such as corals and shellfish, will definitely suffer. And as we continue burning, and if we do not stop, we will end up in a situation in 400 years where the pH of the ocean is -7 pH units from where we are today. And so what is going on? Well, that brings us back to the carbon cycle and the fluxes. And so what is occurring is we have this flux of fossil fuels. Look, it's a 5. Now this wasn't here before the Industrial Revolution. Well, in order to have a steady state, to keep the same amount of carbon in the atmosphere, ocean, and biota, that should be in balance with the continents. But what we see is that the sedimentation rate for carbon is quite low, 0.15, 0.04, and weathering, it's pretty much balanced with weathering for the most part. There is a little discrepancy there, but nonetheless, the fluxes are very low. Both of them are very low, and they're pretty much balancing each other out. So what we have on a yearly basis is this flux of carbon from fossil fuels entering the biota, the hydrosphere, and the atmosphere. And it's continuing to build. And what the Earth is doing is distributing that carbon to all 3 of those reservoirs and trying to minimize the disturbance. But even so, the carbon is building up, and there's really nowhere that's not going to be affected. It's all going to be affected, essentially. And the atmosphere is where much of the CO2 stays. Again, 50% of it stays in the atmosphere. So we'll be discussing climate change a lot more in this class later on in the semester. But I did want to just bring up this model that shows different scenarios and how they will affect the CO2 concentration in the atmosphere. So here we have our long-standing CO2 concentration in the atmosphere over the last 1,000 or 2,000 years. And here we are in our, right here, we're about right here. And so this model, what it shows is, again, different scenarios, such as if we did nothing, which would be here, and if we did a lot and started to bend the curve downward. But what I want to mention is that at least in the last 20 years that I've been exposed to these sorts of data and the models, is that we have all these different scenarios, but the scenario that we continue to follow is the most extreme one. We have all these different scenarios, but it's usually the most extreme one, or actually they keep correcting the models because what we're doing is actually even worse than what they modeled. So that's pretty much our projection, and we can pretty much count on that this is the way that humans have decided to go. And in doing so, what that has done is it's affected, of course, the temperature for centuries. And this is the air temperature. And notice what these curves look like. These look like equilibria curves. If you've undergone a chemical reaction, you have products, or I should say reactants. You have reactants, and the product is higher temperature. The product is also a higher CO2 concentrations for hundreds and thousands of years. And also, we'll have ice melting, of course, and we'll have sea level rise. And again, most people don't realize that sea level rise, most of it isn't from the addition of fresh water from the ice caps. Most of the sea level rise will be due to thermal expansion of that water column. You know, you have in the ocean 4,000 meter depth of water. That's a big water column, and if it warms, it's going to expand. And so to finalize this, again, when we look at the carbon cycle, our main issue is these two fluxes. It's this flux of fossil fuels from the lithosphere that was buried, that was not a part of the cycling between the reservoirs above the Earth's crust. And we have this slow sedimentation rate that is not in balance with the extraction of fossil fuels. So this is what's at play. Until we fix this, these two fluxes, either we start pumping carbon down into the lithosphere or we stop bringing it up, this problem is only going to get worse. And so I hope understanding the carbon cycle and its time scale really helps you understand where we're at with climate change.